All right, let's try this review video again. For some reason, the audio wasn't working on the last video. Okay, so before I get into this, I'm going to go over some of the equations that we're going to use in this unit review. Okay, so starting off with work equals force times distance right here. Okay, so force times whatever distance the object is moving. Okay, work is also equal to change in energy. Now that could be potential energy, that could be kinetic energy. Okay, one thing you will see though is change in kinetic energy. So that's if you see the whole 1/2 mv final squared minus 1/2 mv initial squared. Okay, so dead giveaway that you're going to use that problem is that equation is if you get two velocities. Okay, then you can also set work equal to any of these energies. Well, if work takes energy, you can set work equal to any of these energies here. Now, these equations right here, the PES and the F equals KX, you can go ahead and mark off. We took that off this unit. Okay, which brings us into power. Okay, so power equals work over time. Now, you can also say work equals force times distance all over time. Okay. A couple of things I want you to realize though is also we can do work if we're lifting something. Work equals mass times gravity times distance. Okay, so that's if you're lifting. Or if we look for power and we give you force and velocity, you can use this equation right here. Okay, so now let's go into some problems. Going back up to the beginning, a person lifts, so we're lifting, so gravity is a factor, a 2.5 kilogram knapsack, so there's your mass. Up 0.55 meters, there's your height or your distance. Okay, how much work was being done? Now, remember I talked about if we're lifting something, work equals force times distance, which could be the same thing as saying mass times gravity times distance. So my mass is 2.5, gravity is 9.8, and my distance is 0.55 meters. Okay, so if we multiply all those out, let me pull up my answer sheet real quick. Okay, I get 13.5 joules. Okay, list two scenarios where force is applied to an object but no work is being done. So I'm going to talk about some here. So first, we got to know work equals force times distance. So one is you have to have distance. So if the object is not moving, okay, so if your distance equals 0 meters, okay, that means no work is being done. So if I'm like pushing a car that's not budging or I'm pushing on a wall, I'm exerting force, I'm expending energy. But if I ask how much work was being done, technically it's 0 if the object never even moved at all. Okay, your second scenario is if your force and distance are perpendicular. Okay, so there's two scenarios there you can think about. You can think about circular motion. Okay, so remember your force is attracted towards the center of the circle, and your distance and velocity are actually tangent to the circle. So your force and distance are not in the same direction, so you can't put them in the same equation. Or we had a problem, I believe, in the packet where it was a person carrying an object. So let's just say I'm carrying an object, so I'm using a force to hold the object up, but I'm actually walking towards the right. Okay, so I'm not actually pushing the box to the right. The box is just being held up by me and then going with me in that direction. So my force and my distance are not in the same direction, so therefore no work is being done. Number 3, a gardener pushes a box of tools across the driveway by applying 30 Newton force. Okay, so I have a force of 30 Newtons. Downward at an angle of 20 degrees, so my angle is 20 degrees. How much work is being done? So work is your question mark, and when it moves 2 meters horizontally. So my distance is 2 meters. Now, if you get on the test and you start to panic and you have no idea what to do, try just doing that step. Just try labeling out what you can and then look at your equation list and see if you can figure out what you could possibly use. You never know, that could actually help you figure out which one you can use. So if I were to draw this out, so I'm pushing down on an object, so at an angle of 20 degrees with a force of 30 newtons. Now, I cannot really use that 30 newtons. I need to figure out if the object is moving horizontally, I need to figure out what is the actual horizontal force. Okay, if you wanted to find that, all you gotta do is take the force I gave you and multiply it by cosine of your angle. Now, we also talked about this is anytime we give you an angle, pretty much your equation you're going to use for work is force times cosine of your angle times distance. It just ends up being the same thing every time. So my force is 30, cosine of my angle, which is 20, and my distance is 2 meters. Now make sure you are in degree mode, not radian, and you get 56.4 joules. For how much work is done on a 300 kilogram bobsled, so I have a mass of 300 kilograms. When it speeds up from 30 kilometers per hour, so my V initial is 30 kilometers per hour, but I cannot have kilometers per hour, you need meters per second. So just divide by 3.6, and that gives you 8.3 meters per second. And I speed up to 125 kilometers per hour, so my V final is 125 divided by 3.6. And I'm going to get 34.7 meters per second. Okay, so how much work was being done? So remember we said we have two velocities. So there's a dead giveaway. We're going to use that one equation we talked about. Okay, work equals change in energy. Okay, it can also equal change in kinetic energy. So when you have two velocities, I get really used to using this one. It's the 1/2 mv final squared minus 1/2 mv initial squared. So I'm going to plug in. So 1/2 my mass is 300. My V final is 34.7, and that's squared, minus 1/2 my mass, which is 300, times my V initial, 8.3 squared. Now, hopefully we did our math right. We should get a value of 170,280 joules. And that's your answer. Number 5, a 15 kilogram vehicle. So I have a mass. Okay, I'm just going to start labeling these here now to save time. Is traveling at 25 meters per second, and then brakes suddenly applied and it slides to a stop. So my VI was 25, and my VF is going to be 0 meters per second. Now the braking force between the tires and the road is 7,100 newtons. So my force, now it's going against you, so technically that's a negative 7,100 newtons. Okay, how far will it slide? So that means you're looking for distance. Okay, so it says use the work energy theorem. So remember we said work equals change in energy. Well, I have two velocities, so I'm going to use that same equation we used in number 4. But I'm also dealing with force. Well, we remember work equals force times distance. So I can just plug that in for W and set that equal to the 1/2 mv final squared minus 1/2 mv initial squared. Now the good news is your V final was 0. Okay, so that means you can mark off this whole thing right here and put 0. So now I get to plug in. So force is going to be negative 7,100. Distance, I don't know. Okay, so 0 equals 0 minus 1/2 my mass, which was 1,500. And my initial velocity is 25, and that is squared. So be careful with your math. Divide both sides by negative 7,100, and you should get a distance of 66 meters. Okay, moving on to number 6. So number 6, it says an applied force. So my applied force accelerates a 2 kilogram object. So you have a mass over 5 meters. So there's your distance. And I actually have a 2 Newton frictional force. So frictional force right here. So calculate the work done on the object. So whatever the applied force is, that's the thing that's actually doing the work. Okay, so if I want to do work equals force times distance, okay, it's just the applied force. It's whatever's doing the actual applied force. So it would be 10 times my distance, which is 5 meters. So 10 times 5 gives me 50 joules. Okay, now it says calculate the acceleration of the object. So remember acceleration equation. Acceleration equals F net over mass. F net means total force now. So now we actually got to take that frictional force into account. So if I'm applying 10 newtons of force, but 2 is going against me, so 10 minus 2, over my mass, which is 2 kilograms. So 10 minus 2 gives me 8, divided by 2 gives me 4, and this meters per second squared. Okay, number 7, how much power is needed? So we're looking for power. is needed to push a loaded cart with a force of 400 newtons. Okay, so there's your force. Through a distance of 10, I'm assuming that's 10 meters, so there's distance, and I gave you time, which is 3 seconds. Express your answer in watts and horsepower. So we know power equals work divided by time. So in this case, I don't necessarily know work, but I can solve for work. So we can just go ahead and say work equals force times distance. So I'm just going to plug this in for W over T. Okay, so force is going to be 400. My distance is 10. And my time is 3 seconds. Okay, so that should come out to be 1,333.3 watts. So there is your first answer right there. But I want it in horsepower. So remember, 1 horsepower equals 746 watts. So what I'm going to do is I'm going to take that 1,333.3, I'm going to divide it by that 746, and I'm going to get 1.8 horsepower. Okay, next question. What speed would a 50 kilogram girl, so I have a mass, have to run to have the same kinetic energy? So key phrase there is same kinetic energy. Of a 1,000 kilogram car, I have another mass. Okay, so I'm going to say label this the mass of the girl and mass of the car, traveling at 2 meters per second. So this is the velocity of the car. That means I'm looking for what is the velocity of the girl. Well, they have the same kinetic energy. So basically we're saying KE equals KE. Okay, the car and the girl have the same kinetic energy. So we can just set them equal to each other. So 1/2 mv squared equals 1/2 mv squared. So we're just going to plug in. So 1/2, the mass of the girl is 50. But I don't know the velocity of the girl, so I'm going to leave it as V. And then the car side, so 1/2, my mass of the car is 1,000, times the velocity of my car, which is 2. And that's going to be squared. So be careful when you do this. Get V by itself and then square root both sides. And you should get a velocity of 8.9 meters per second. Number 9, a 2.5 kilogram textbook. Okay, I have mass. Rests on a shelf 0.75 meters above desktop, so I have height, which is in turn 0.80 meters above the floor, so it's also height. What is the gravitational potential energy of the book with respect to the floor? Now, I have seen some students do this. They start doing the PE plus KE equals PE plus KE. Okay, now if the book actually moved, if it fell off, it went towards the floor, if it was raised up, if it changed positions, then you could use that. But right now, the question is only asking, what is the potential energy of the book? It's just sitting there. Okay, so try not to make the problem more complicated than it actually is. So potential energy is mass times gravity times height. So my mass is 2.5, gravity is 9.8, and height, I'm actually going to combine those heights because it's sitting on a shelf on top of a desk, and the desk is 0.08 meters above the floor. So just combine those, and that gives you 1.55. Okay, multiply those out, and you get 38 joules. Okay, number 10, a 10 kilogram sack of grain is raised, so I have a mass. Is raised up to a storage room 50 meters above, so I have a distance or a height. Above the ground floor of a grain elevator, how much work is being done? Okay, so remember we're lifting something, so work equals mass times gravity times distance. So I'm going to plug in, so mass is 10, gravity is 9.8, distance is 50. Multiply those out, and you get 4,900 joules. Now, what is the gravitational potential energy of the sack of the grain? Well, we know work equals potential energy as well, which equals mass times gravity times height, which is just the same thing we just calculated right above. And so instead of saying distance, we're just saying height now. So it comes out to be the exact same thing, 4,900 joules. Okay, now I'm going to draw, so here's a little pulley. Okay, here's the rope. We're pulling this sack of grain up. So here's a sack of grain sitting up 50 meters. It weighs 10 kilograms. So when I pull it up and it's sitting there, okay, all you have is potential energy. Okay, it's not moving. It's just sitting there. It has height. Okay, so if that's all you have, that means potential energy equals your mechanical energy. which is the total amount of energy you're going to have the entire way. Now let's say that rope breaks, like in part C it says, what is the kinetic energy of the sack of grain just as it strikes the ground after the rope breaks? So once that box falls down, okay, right before it hits the ground, all of its energy is just transferred to kinetic. Okay, because now it has no height, it has just purely velocity when it hits the ground. So that means whatever mechanical energy you had up here is going to be the same thing down here. So now my mechanical energy is just kinetic energy. Okay, so that's a real important concept to remember, is that your mechanical energy does not change. It just shifts between potential and kinetic. So whenever it hits the ground, we're not going to lose energy. So whenever it hits the ground, your kinetic energy is going to be the same thing. So 4,900 joules. It just shifted from potential to kinetic. D, what is the velocity of the sack of grain as it hits the ground? Well, if I know my kinetic energy now, I can set this 4,900 equal to 1/2 mv squared. So my mass is 10 kilograms. Velocity I don't know, so I'm going to leave it as v. So solve for v, and you should get 31.3 meters per second. Now, number 11, it says an egg falls from a nest at a height of 3 meters. When it hits the ground was the impact of the velocity. Now is we have an object that was sitting in a nest and then it actually fell to the ground. So now we actually have two heights, or two positions. Okay, so now this is when we can do the whole PE plus KE equals PE plus KE. Okay, so I'm going to draw a poor nest. Okay, sitting on a branch and then an egg in there. Okay, so this egg is just sitting in the nest, and then for some reason it falls out and it's going to hit the ground, okay, 3 meters down. Now, when it's sitting in the nest, okay, so you got to look at your PE plus KE. So let's say this is before, this is after. Okay, so left side's before, right side's after. So I'm going to kind of clear this up so I have some room. So before the egg leaves the nest, okay, it's just sitting there. It has height, so it's got potential energy, but it's not moving. So that means we can mark out kinetic energy. So that's going to be 0. Now, once it falls and it hits the ground, whenever it hits the ground, potential energy goes to 0 because now it no longer has height. So when it hits the ground, it is purely kinetic. So therefore, we can set those equal to each other. So potential energy in the nest equals kinetic energy when it hits the ground. So let's plug in our equations. So mass times gravity times height equals 1/2 mv squared. Well, if m is on both sides of the equal sign, it has to be on both sides of the equal sign, and it has to be the same object. Okay, so it's the same egg before and after. Mass does not matter, so you can just cross it out because it would just basically divide out on its own anyway. So I'm just going to plug in now. So gravity is 9.8. My height is 3 meters, equals 1/2 v squared. Okay, so get v by itself, and we should get a velocity of 7.7 meters per second. So that's actually how you can solve that problem with just one number. All I gave you was height, because we marked out so much, all you needed was 1. Number 12, if a child has more gravitational potential energy at the top of the slide than the kinetic energy at the bottom of the slide, what caused the difference in energy, and what form of energy was it given off as? So we have a slide. So at the top, okay, we've got a child, boy or girl up here. It has purely potential energy. Okay, let's just say it's 10 joules just for the sake of this problem. Now, for some reason, when that child gets to the bottom of the slide, now they have purely kinetic energy. But for some reason, let's say it's 8 joules now. So we want to know, where did that 2 joules go? So what happens is, in a real world, when you slide down something, okay, you will lose energy to friction. Okay, so friction is causing that loss of energy. Now, energy is not just disappearing completely. What it's doing is it's being transferred to heat. So when you slide down something that has a lot of friction, you can feel that heat, okay, as it's trying to stop you. So all it was that 2 joules was just transferred to heat through friction. 13, a toy car with a mass of 5 kilograms is pushed with a force that varies with the distance. Okay, so I have a graph. So remember graphs, what you need to know is a square or rectangle. If you want to find the area of that, it's just base times height. And if you want to find the area of a triangle, it is 1/2 base times height. So I'm going to go ahead and just create my rectangle and triangle. That just makes it easier. I'm going to find the area of those. Okay, so my square, my rectangle has a base of 3 and a height of 8. So 3 times 8 gives me 24. Okay, my triangle has a base of 2 and a height of 8. So 2 times 8 gives me 16. And half of that would be 8. So it says in part A, the total work done on the car while being pushed from 0 to 5 meters is, okay, so I just got to add those up. So 24 plus 8 gives me 32 joules. Okay, what is the toy car's final velocity if it started with initial velocity of 2 meters per second? Okay, so I want to know what VF is. I gave you VI. Okay, now remember we solved for work up here, so that is our energy. So remember work equals change in energy, which equals, if I have two velocities, that's our dead giveaway, 1/2 mv final squared minus 1/2 mv initial squared. So I already know my energy is 32 equals 1/2 my mass, which we said was 5 kilograms. Velocity final, I don't know, I'm going to leave it as VF, so VF squared, minus 1/2 my mass, which was 5, times my initial velocity of 2, and that is squared. So just be careful with your math. You should get a final velocity of 4.1 meters per second. Okay, now what I actually want to do is I actually want to talk about some conceptual stuff, because I know a lot of students, they do great on the actual math part, and then it's the conceptual multiple choice stuff that gets you. So I want to kind of talk about some of those things. Okay, so there's some things that we can ask. So one, when we start talking about manipulatives as far as equation goes, say, so kinetic energy equals 1/2 mass times velocity squared. So the things you got to watch out for here is if I were to double my mass, okay, my kinetic energy would also double. Okay, there's nothing special about mass. If you double the mass, kinetic energy just does the same thing. It's just going to follow suit. If you make the object bigger, okay, the kinetic energy is going to get just as big. Now, the one thing you need to be careful for is velocity, because that's squared right there. If I were to actually double velocity, okay, so 2 squared actually becomes 4. So that means my kinetic energy actually goes up. Okay, oops, put it down. Should put it down here. Let me clear that up real quick. Okay, my kinetic energy is actually going to quadruple. Okay, so that's something you got to be really careful for on that part. And there's not really much special about potential energy. You just need to know that potential energy is mass times gravity times height. So the key thing about potential energy is it deals with height. Kinetic deals with velocity. Both have mass, okay, but kinetic is movement, potential is height. So if you have height, you have potential. If you have movement, okay, or velocity, you have kinetic. Okay, so now let's talk about power. Okay, so power, okay, is dependent on work and time. Okay, so what usually determines your power is how quickly you can get it done. So say I have 2 people trying to get something done. Okay, so but it takes the same amount of work. So let's just say it takes 100 joules to get done. So I do it with 100 joules of work and you do it with 100 joules of work. Okay, but I do it in 5 seconds and you do it in 10 seconds. Well, if I did it in a quicker time, okay, I'm going to have more power. Okay, because that power is able to do the job more efficiently. Okay, so just make sure you know those relationships there. Okay, so now what I'm going to talk about is conservation of energy. Okay, or conservation just in general. Okay, there's some things that are conserved always in physics. One thing would be mass. Okay, unless something's breaking, like falling apart, like a 300 kilogram bobsled loses a blade or something like that, which is not going to happen as far as we're going to go over. Okay, mass is always being conserved. Okay, it's always the same. Also, energy. Now, it's not potential and kinetic. That stuff can move, but it's always your mechanical energy that is the same. The total energy is mechanical energy. That stays the same. Also, in the last unit, we talked about momentum. Remember, individual momentums can change all they want, but total momentum is going to stay the same. Okay, now I want to talk about some actual scenarios where you're actually doing like the whole PE plus KE, okay, because I see some confusion there. So let's start off like real simple, like what we've been doing, like a roller coaster or something falling off. Okay, so when you're at the top, let's say this roller coaster, okay, what you have is potential energy. You haven't started falling yet. Okay, so there is 0 kinetic energy. So kinetic energy is gone. Okay, now potential plus kinetic equals your mechanical energy. So that means at the top, your potential energy equals your mechanical energy. Now, as you start falling, your potential energy is going to start going down because you're losing height. And then as you go down, your velocity is going up. So your kinetic energy is going up. So when you reach the bottom of that roller coaster or hill, you are purely kinetic energy. So potential energy is now gone. Okay. Regardless, that is still equal to the mechanical energy that you had before. Okay, so when you're going to do the whole PE plus KE equals PE plus KE on this problem, okay, so at point A, so let's say this is point A and this is point B. And we'll say this side is point A, this side's point B. I get to mark off kinetic energy at point A because it hasn't started falling yet. Okay, and then when it reaches the bottom, I get to mark off PE, okay, because it reaches the bottom, there's no potential energy. So I get to mark off 2 in that situation, but don't always assume you get to mark off 2. So an example where that is a possibility is, let's take the same roller coaster, but now let's add a loop. So here's point A, here's point B. Okay, so I'm going to do the whole PE plus KE equals PE plus KE. So at point A, I haven't started falling yet. I have potential energy. I do not have kinetic, so I get to mark that one out. That becomes 0. Now at point B, I actually do have height. I'm not on the ground, so I cannot mark off potential energy there. And then when you're in that loop, you're not still, okay? Because if you did, you would just stop, or you'd like fall, or you're stuck. So you actually do have kinetic energy there, so I only got to mark off 1 thing. Okay, so just don't assume that you can always mark off 1 thing. I'm sorry, 2 things. Another scenario you can look at is launching something up. So let's say I have a ball, I launch it up in the air, and I want to know how high it goes. So this is point A, this is point B. So I'm going to do the whole PE plus KE equals PE plus KE. Now at point A, I'm on the ground, I'm launching something up, so that means I have 0 potential energy and I have pure kinetic. Now when I reach the top, okay, the ball's not going to just keep going and going and going. It has to stop. Now, when it stops, it definitely has height, okay, because it's off the ground. But when it stops, that's the key word, is your kinetic energy gets to go to 0. Okay, so that one we actually got to mark off 2 again. So those are the 3 scenarios that you'll kind of run into as far as the PE plus KE equals PE plus KE goes. So hopefully that kind of helped you out a little bit, and let us know if you have any questions.